All right, pilots, this is your next set of flip notes. It's based on standard 6.P.1.2, which is the long way of saying visible light, EM spectrum, and wave behaviors. Remember with flip notes, you have these four essential things you can do. You have the power to pause the video at any time. That allows you to copy down the notes on the screen. You're able to go back and rewind. It's just like raising your hand in class and saying, what did you just say? That is that. If something is confusing, unclear, or just seems nuts, please write down that question somewhere and ask me when we get together in the class meeting tomorrow. And remember, these notes will be for all the assignments this week. So if you do not use these notes, the assignments this week are going to be very difficult. You have two note collection options. I left you a Google Doc that has the template of these notes. They go in order of the slides. So if you want to like have the YouTube video in one slide and the notes template in the next tab, you can flip back and forth. Or you can go old school, write on a piece of paper. That's up to you. But remember, taking notes are not optional. Even though you don't turn these in for a grade, all the grades this week come from these notes. So if you do not do these notes, all your grades are going to suffer because this is where the content or the answers come from. First, we're going to start with wave behaviors. Okay, so before we moved into the standard, we talked about the different types of waves, different types of wave movements. Now we're into the standard of how do waves behave. Just like you behave or don't behave, waves do the same thing. But when we talk about it in science, it is how waves acts or behaves. And when we say this, we mainly are connecting with how do they behave when they come in contact with a piece of matter, which is also known as a medium. So how do waves act when they come into different mediums? And that's what this first section will be all about, how waves do different things when they come in contact with different mediums. The first wave behavior is reflection. Okay, the definition of this is the bouncing back of a wave after it strikes a barrier. Okay, my two images are the examples. Are an echo, like if you're speaking and you hear the echo, okay, that's the bouncing back of a wave off of a barrier. The barrier would be a wall or something like that. Or if you look into a mirror and the reflection comes back and you see your pretty little self in the mirror, that's also the wave using reflection to give you that image. The next wave behavior is known as refraction. Refraction. And this is the bending of a wave as it enters a new medium. So this one is interesting. You need two different mediums because it's leaving one medium, entering a new medium, which means you need two different mediums. Remember, mediums can be solids, liquids, gases. Okay, and examples I show you down below is the prism. You have white light entering the prism, and then you have the refraction, which is the rainbow coming out the other side of the prism, which we'll talk more about in a little bit. And if you sat on a pool side and you put your foot into the pool and you look down, you might look like your leg is not connected to your body in the proper way. And that is refraction because you're looking from air into water. So that's one of the most common is air into a liquid, but also prism is air into a piece of glass or plastic. The next wave behavior is diffraction. This is the least common that we'll talk about, but we still are going to address it. Diffraction is the spreading out of a wave through an opening or an obstacle. Okay. My example, as you can see, is if we were sitting in our classroom or if you were sitting in your room, okay, and you had the lights out in the hallway, if we opened our door, you notice that the light from our room would go through the door, but also spread out as it left through that obstacle. Okay. This happens with sound as well. If you think about a stadium, okay, the noise of a stadium would leave through the doors, but it actually spread out when it gets into the parking lot. So diffraction is the spreading out of a wave. Most commonly it's light because light comes through something and then spreads out, just like a flashlight. A flashlight is showing diffraction because it comes out in this small hole and then it spreads out as you use the flashlight. The next wave behavior is known as transmission, okay? Transmission is the passage, which means it lets the EM wave through a medium, okay? An example of this is if you look out the window and light comes through that, That is light through the windows using transmission to get through your window because the window is not interfering with the wave coming through. So it transmits through. Okay. Next wave behavior is absorption. And this is the disappearance of a wave into the medium. For example, when you make a shadow, your body's absorbing the light, and that is showing how absorption works there. A solar panel absorbs lights. So if something is absorbing something, it allows the wave to disappear into that medium and not let it get through. The next is scattering. Scattering, think about like if a bug scatters, it goes out in all directions. This is kind of the same thing. Scattering is the spreading out of light in all directions because the particles reflect and absorb. There's a combination of different wave behaviors making scattering happen. An example would be a stained glass window or light hitting the surface of the ocean because the light will go in all directions. And with stained glass, you get to see all these different colors, and some light comes through and some light does not come through because it's getting scattered around. So that was a lot of different behaviors. I'm aware of that. Make sure you have the definitions down. We will dig deeper into these as the week goes on. The next part of the notes is we're going to talk about the EM spectrum. We're not going to talk a lot about the EM spectrum just because we're going to get into more of that next week, but we're going to focus on light and color. But to be fair, we have to talk about the EM spectrum if we're going to talk about light. So the EM spectrum has 7 types of EM waves on it. Okay, EM stands for electromagnetic. Hopefully you didn't forget that over track out. Each of the types of waves have a different wavelength and frequency. So you can see that the words we learned before we tracked out are coming back into this unit because they're all part of waves. And in order, it is radio waves, microwaves, infrared, visible light, ultraviolet, also known as UV, X-rays, and gamma rays, and they can go either way. Most of the time you'll see them radio to gamma, but sometimes you'll see them gamma to radio. And here's a picture of the EM spectrum. And you can tell that the radio waves have these really big wavelengths, which means their frequency is really low. And then you can see that gamma rays have really small wavelengths, which means their frequencies are very high. As you move from radio to gamma, the energy increases, the danger actually increases. If you look at the right side of that picture, X-rays and gamma rays are actually quite dangerous, but radio and microwaves are not. And also the amount of heat that is given off by these waves increases dramatically. Gamma rays give out a lot of heat and radio waves give out little heat, and we'll talk more about that next week. But let's focus on visible light. It's the only part of the EM spectrum a human can see without a tool. I mean, obviously the tool will be your eyeballs, but it's the only part of the spectrum. Like you can't see a microwave or a radio waves. You can't see an X-ray unless using an X-ray machine. But visible light, we see it every day. It's how we see. Each color has a different wavelength and frequency. This is how all colors are different. You'll see that as a quiz question coming up. How are all colors different? It's all based on wavelength. And then you might have heard of Roy G. Biv before, possibly in art class. It stands for red, orange, yellow, green, blue, indigo, and violet. But that is also the light spectrum. So if you go from left, like red has the biggest wavelength and violet has the smallest wavelength. They're not too much difference, but they are different. That's the order of the rainbow, and the rainbow is ordered that way because that is the visible light spectrum. There is a tool that is used to figure out how light is spread into the different colors. Okay, so if you didn't know, all the light coming from the sun is known as white light. White light is all of the different colors of the rainbow put together. So all light is white until something else happens, a different behavior. Now this tool uses refraction. If you remember, refraction is the bending of waves. So as the light enters one part of the prism, which is like a triangular prism, okay, it will bend in the material the prism's made out of to separate that white light into the different colors, because all colors bend at different angles, and because they bend at different angles because they have different wavelengths. Okay. Let's get into reflection and absorption. Okay. These two wave behaviors are really key on seeing color, because the color of an object is determined by the wavelengths it absorbs and the wavelengths it reflects. So if you look outside and you see green grass, it is based on the wavelengths that that grass is absorbing and then reflecting. The color you see of an object is the wavelength it reflects. So all other colors that you don't see are being absorbed by those objects. White, we're talking here about how you see white objects. White objects, like I said, it's called white light for a reason because white objects reflects all colors and absorbs none. All colors are reflected and none are absorbed because if you see all the colors together, you see white. Now, on the opposite end of that, how we see black things is the complete opposite of white. Black objects absorb all colors and reflect none. If you think about solar panels, blacktop, the reason why they get so hot is because all of the light is being absorbed, and light does carry heat. So the more it absorbs, the hotter it will get. And if you reflect none, think about your body. There's a reason why you make a black shadow is because you're reflecting no light behind you. You're absorbing it all. And then with any color in particular, I talked about that green grass. Any color reflects what you see, and all the other colors are absorbed. I'm going to show you some images to help explain that. So for example, this red apple, okay, the sunlight is hitting this red apple, and then it absorbs all the colors except red, and it reflects red, so you get to see a red apple. Okay, there's all the different cubes, same things happening with those cubes. So for example, the orange cube, all the colors are being reflected or absorbed except for orange, which you see reflected back to you. And then there's those prisms on the bottom with the white showing you how white light strikes it and how you see that particular color. It's just reviewing what we just put in our notes. The last part of this, I know these are a lot, but we're going to get these in and then we're going to use them. The last part of this is materials and light. And materials are how different materials interact with light. So we're going to talk about first transparent materials. And transparent materials are things that most of light strikes them and passes right through them. Okay, this is caused by the wave behavior transmission because it transmits light, lets it go right through. An example of this, clear glass, like your glasses, the watch face, any glass cabinet, windows, you see right through them because the waves are coming right through them. Imagine if your glasses were not transparent, you'd have a really hard time seeing. The next type of material is called translucent. Okay, materials that are translucent, they transmit some light, but also cause it to spread in all directions. This is caused by the wave behavior scattering. Okay, and examples of this would be a stained glass window or tinted windows. Also, like sunglasses have translucency to them. Or like if you look at tinted windows in a car, if you're outside of a car and someone's inside of a car with tinted windows, you see their silhouette, but you don't see their features. Stained glass, if you look through stained glass, you don't clearly see through it, but you could do kind of see through it. Okay, so it's one of those things that some get through, but not all. And the last type of material is known as opaque. Okay, this does not allow any light to pass through them. It's either caused by one of two things or both of those things working together. It's either reflection, absorption, or both. Either it's absorbing all, it's reflecting all, or a combination of those two things are happening where no light is getting through them. Examples of this would be a brick wall, a wood floor. I have a picture of a dice right there. That dice, you can't see through it. That apple, you won't see through an apple. Okay, but if you can't completely see through it at all, that would be opaque. I know these were a lot of notes. Make sure you get those down, and we will be discussing these this week. So have any questions for me written down, and I look forward to seeing you tomorrow. Till then, I hope all is well.